Okay, so we're here today in the lab in Montgomery College. We have our labs and our safety coats on due to safety precautions, and we were going to attempt to use this machine here, but due to some leakage around this gasket, we've been having trouble keeping the pressure in. So what we're going to do is use that Hoffman apparatus over there, but I still want to go ahead and explain this here. So just for a little clarification and what's going on inside this machine, I wanted to give an example of a diagram and an example of the inside plate. Now let's start with the inside plate. This cross-hatched pattern is laid on there in order to give more surface area for the gas to bubble on, and these three holes are laid out for gas equalizing holes. Now what this plate lies is this pink line here is going to be our 6 plates inside, filled with our 10% KOH by weight, and we'll have our anode and our cathode to apply electricity in and out. And then what happens is our gas is going to bubble up here and exit out this hole in our 2H2 and our O2 format, going into the water reservoir, in which it's going to bubble through some pure H2O. Upon bubbling through some pure H2O, it'll go out this tube, and we would have liked to send it to a torch and demonstrate combustion, but due to safety reasons, that's not going to happen today. Okay, so our water is going to flow in here. It's going to be normal H2O, and on the other side we have a gas outflow tube. Now our anode and our cathode exist here, so we're going to put 12 volts and 60 amps would have gone in here and came back out here, but through the process it would have exchanged electrons through the 6 plates, generating our hydrogen ion and our oxygen ion. Both being diatomic, they would come out H2 and O2. And these gases would bubble up this tube through the bubbler. Now the purpose of the bubbler is to keep backflashing from occurring when the gas flows up through the water and down through this tube to the Bunsen burner. There we would have burned our 2H2 and our O2, giving us 2H2O. Okay, so I wanted to draw a little emphasis to this bubbler here, because one might think you can just hook the gas tube directly to the Bunsen burner and start a flame there. The problem is hydrogen gas and oxygen gas have such a high, low flash point that when they're combined, they can spontaneously explode. So what we did here is we ran our gas tube down through the water, so when it bubbles, the gas stays separate from our area of production. So essentially when we light this will help prevent a back pressure from flowing back in here and just blowing this thing apart from the inside. So here we have our DC voltage source. Now the reason we're using DC voltage is because it gives higher efficiency as opposed to AC current. Now this machine here bridge rectifies your AC current here with a diode, forcing the current to flow in one direction. Now we also have a few options here. We can go 200 amp, 40 amp. We're going to use the 40 amp due to our the ampicity of our plates, and 12 volts. Like I said, we have 6 plates, 2 volts per plate to keep efficiency in order. Now ampicity comes down to basically amps per square inch. Stainless steel has an ampicity that calls for about 0.5 amps per square inch. So we went ahead and made 11 by 11 plates to give us about 120 square inches. So we don't build too much resistance, too much heat. We keep this thing in order. And over here, Tien, my friend's going to connect the positive terminal and the negative terminal, red being positive, black being negative. And when we turn this thing on, current will flow in this way and out this way, and our electrons will flow in this direction. Okay, so what we have here is our Hoffman apparatus and our DC voltage source. It's currently not on, so we're not producing any gas. But what's going to happen is our positive terminal, which we'll call anode, is going to produce oxygen gas. And at the negative terminal, the cathode will produce hydrogen gas. Now I do want to note that we're producing twice as much hydrogen as we are oxygen. And this happens through the oxidation, which gives you 2H2O, 1 O2, and 4 H plus ions for 4 electrons. Now our reduction reaction is going to be 4 H2O, 4 electrons, giving you 2H2, and 4OH. And this can be indicated by the color. We have a universal indicator in here, so it can be indicated by the color in each reaction. Now, this being red is indicating an acidic reaction due to the 4H plus ions, which is the characteristic of acidic reactions. Now, the 4OH ions being a characteristic of basic reactions is indicating a blue color, blue being basic. Now, the each cell potential being indicating the spontaneity of the cell is going to be minus 0.83 volts for our reduction reaction, being the cathode, and this goes cathode minus anode reaction, and our anode being plus 0.123 volts on the oxidation reaction, giving us an overall cell potential of 2.06, which is a non-spontaneous reaction because it is negative. So here you can notice that the indicator's already changed colors. This reaction's already been started, and right now we have a difference of 2 milliliters, indicating twice as much hydrogen being produced as oxygen. Now if you look here, we have a platinum electrode, and we use platinum because it's an inert molecule, so we don't have to worry about it taking part in the reaction. Versus something like copper would in a sense turn the water black, because copper wants to take place in the reaction as well. But you can see our oxygen bubbles going up the tube, and right here you can actually see that twice as much hydrogen is being produced here, because over time you'll start to notice that this level and this level do not match. So we can expect this to empty twice as fast as this. Okay, so we're back after 5 hours, and this Hoffman apparatus, or otherwise known as electrolytic cell, has been running since, and after 5 hours we've come to a total of 11 milliliters of O2 and 23.8 milliliters of H2. Now you can see the difference here, and it is almost about twice as much H2 as we predicted as the O2 produced. Today we've been able to demonstrate how an electrolytic cell, or the process of electrolysis, which is generally defined as using a direct current to drive a non-spontaneous process, works. As you can see, this was a non-spontaneous process, and in the process we produced gas, which in return can be used for a spontaneous process. You see, H2 and O2 can be reacted to produce an equivalent amount of energy as you put in to produce these gases as they produce when they react together. This application falls in fuel cells, essentially, that use these two gases without combusting them and do a reaction sort of similar to a galvanic cell, where they run electrical current between producing mechanical or electrical energy. So I'm Steven.
I'm Noah. I'm Tien.
And we want to thank Dr. Chang for sponsoring this video. And from Chem 135, thanks for watching.